Hi, good morning, everyone. Are there any questions? All right. Last time we talked about the tautological implications. Next week I'll give you some questions to work on today on the slides as exercises, and I'll post a few questions for assignments as well by the beginning of next week, so you can sort of start with the first assignment, at least the first few questions. So we talked about the notion of tautological implications when you have a set of formula in general. Gamma tautologically implies a formula A if for any state that satisfies gamma, it satisfies A. So that was the definition. Now let's look at the following proposition that says if A1, A2, AN, so these are the set of the hypotheses. We agreed that when we have finitely many formulas, we just don't write it as a set and just list them as hypotheses. A1, A2, AN tautologically implies B. Then this statement, A1 and A2 and all the way to NAN, implies B is a tautology. So how do we prove this? There are different methods that we could use. So I'm going to assume what we have. That is, assume A1, A2, AN tautologically implies B. Now, one way to do this is to prove by contradiction. So let's prove by contradiction or contradiction method. So suppose A1 and A2 and AN implies B is not a tautology. What does this mean that a formula is not a tautology? It means that there is a state that assigns false to it. So this means there is a state. Let's call that state. I'm going to give this specific name. Let's call it B0, such that V0 of this formula A1, A2, AN implies B is false. Now, this formula implies B. It can only be false if V0 of A1, A2, and AN is true and V0 of B is false. But this is a contradiction. Why? It's a contradiction with the assumption. The assumption says that A1, A2, AN tautologically imply B. So any state that satisfies A1, A2, AN should satisfy B. Here we have V0 that satisfies A1, A2, AN, but does not satisfy B. So let me just explain a little bit more. So this implies V0 of A1, V0 of A2, and V0 of AN. They're all true, but V0 of B is false. So V0 is a state that satisfies A1, A2, AN, but it does not satisfy the formula, the formula B. But this is a contradiction with our assumption, which was saying A1, A2, AN tautologically implies B. Right? Any questions? All right, let's move on to the to few exercises. Here, prove that A and B tautologically imply A. This is again a trick question because A is one of the hypotheses, right? So any set that contains a formula A would tautologically imply A, because when you want to, you can conclude A if A is your hypothesis. So, but you could write the proof precisely. Now, 2 says that the formula is A implies B implies C, tautologically implies C. The third one says P or Q tautologically implies P implies Q implies Q. 4, if A tautologically implies bottom if and only if bottom is a negation of A is a contradiction. Note that this says negation of A is a negation of A is a tautology, which means A is a contradiction. And fifth one says that if you have infinitely many hypotheses, A1, A2, all the way to A infinite, well, infinitely many of them, then together they tautologically imply A7 implies A12. I randomly chose those numbers actually, but so I can prove one of them. For example, I can maybe prove number 2. Just how do we show this? We need to show that any state that satisfies all of these 3 formulas would satisfy C. So suppose V is a state such that it satisfies all 3 formulas. That means V of A, V of A implies B, and V of B implies C they're all true. Now we need to show that V of C is true. Again, there are different methods. You could prove this by contradiction, assume V of C is false, and then you get a contradiction, or you could prove it directly, because you can argue like this: since V of A and V of A implies B, they are true, we conclude that V of B has to be true, right? Otherwise, if V of A is true and V of A implies B is true, then V of B has to be true. Because otherwise V of A implies B would be false. So if V of B is true, all right, since V of B is true and V of B implies C is true, we conclude V of C is true. And we are done. For the 5th one, note that, okay, this looks a little bit different, but it's basically trivial. Here we have infinitely many hypotheses. A1 is a hypothesis, A2 is a hypothesis, A3 is a hypothesis, and so on, right? So I wrote this so that you know that the set of hypotheses doesn't have to be a finite set. Now, for example, you can tautologically imply A7 implies A12. How? How do you show this? Again, you need to only prove that we have this formula is true for the state V that satisfies the hypothesis. So suppose V is a state that satisfies the hypothesis, that is V of AIs or V of AN. So suppose V is a state such that V of all of the AIs or ANs, I don't know whatever you want, this is true for all natural numbers n. Now we need to show that we have show that V of A7 implies A12 is true. But this is trivially true because V of A12 is true. It's in fact true implies true, right? Trivially true because V of A12 is true. So as you can see, most of them are, I mean, they're all very easy. You just need to be able to write the definitions properly. All right, let's move on to the next theorem. Suppose now we have two sets of formulas. One of them is sigma, the other one is gamma, and sigma is a subset of gamma. So that means all the formulas in sigma are included in gamma. If sigma tautologically implies A, then gamma tautologically implies A. Note that what this theorem is saying that is that if a set of hypotheses can tautologically imply a formula, you can also get the formula A from more hypotheses. Sigma is a subset of gamma means gamma has more formulas in it. At least has all the formulas in sigma. Maybe they're equal, but at least has every formula in sigma. So if you increase the number of your hypotheses, you can always prove what you could prove with the previous hypothesis. Just don't use the new hypothesis, right? So how do you prove this? So the proof is basically obvious. We're supposing that sigma is a subset of gamma. Assume now that sigma tautologically implies A. What does this mean? This means that for any state that satisfies sigma, it is going to satisfy A. Right? So that's our hypothesis. Now we want to show that gamma tautologically implies A. Yes. What if we have like negation of A or like bottom? It doesn't matter. I mean, it doesn't. If you have negation of A, or then you can get negation of A. So, yeah, this is for any formula A. Doesn't matter what formula A is. It could be bottom or anything. So this is for. Let me add that actually. This is for any A. And when I didn't say what A is, that means just arbitrary A. So, all right, we wanted to, so those are the hypotheses. We are assuming sigma is a subset of gamma, and we assuming that sigma tautologically implies A. Now we want to show that gamma tautologically implies A. So take a state V that satisfies gamma. Now we need to show that V satisfies A. So V is a state that satisfies gamma. What does that mean? V gives true to all the formulas in gamma. All the formulas in sigma are included in the formulas in gamma. So if V gives true to all the formulas in gamma, obviously it's giving true to all the formulas in sigma. So V satisfies sigma. So V satisfies sigma by our assumption means V of A is true, since sigma tautologically implies A. We are done. We wanted to show that any state that satisfies gamma satisfies A. Any state that satisfies gamma would satisfy sigma as well. And since sigma tautologically implies A, that means that state satisfies A. So an obvious proof. Now, show that the converse of this statement is false, meaning that it is not true. So let me write this down. If sigma is a subset of gamma, show that it is not true that if gamma tautologically implies A, then sigma tautologically implies A. Why? How do you show something is false? You find a counterexample, right? That means find a specific sigma and gamma and a specific formula A so that this does not hold. Can anyone think of any such objects? So it's an exercise. So I'm going to leave it for you to think. But for example, think of the case that gamma contains a single formula, let's say a propositional variable P, and sigma is empty. It's the empty set, right? Empty set is a subset of a singleton. Or any formula. I wrote P, but you could have written anything you want. But now note that if my A is also the formula P, then P tautologically implies P. As I said, this P could be any A, any formula. Just pick the specific one. Anything other than top is going to work. As long as your formula that you pick is not a tautology, it's going to work. Note that so this means this holds. But does empty set tautologically imply P? This means that P is a tautology. A variable is never a tautology. Variable can take true or false. So this is false. You see, what this is saying is that if I can prove A, not prove, but I can tautologically imply, so it's going to be same as proving. If I can conclude A from the set of hypotheses gamma, then I can conclude A from less hypothesis. No, it's not true. Maybe those hypotheses were necessary. You can add more hypotheses and you can still prove the same thing, but you cannot just prove something with less hypothesis. In general, it's not true. So this was you can write the proof properly. More exercises. Show that if A is in gamma, then gamma tautologically implies A. This is again kind of a trick question because it's basically obvious, right? If A is in gamma, that means A is a hypothesis. So A is here. If A is a hypothesis, you can conclude A, right? So this is basically trivial. But again, what I want you to do is to try to think of this as with the formal definition, right? So you take a state that satisfies gamma, that means it gives true to all the formulas in gamma, but A is in gamma, so that state is giving true to A too. Therefore, it satisfies A. So we are done. Let's show that if A is in gamma, then A union negation of A is not satisfiable. This is a set of formulas, right? We defined the notion of satisfiability for a set of formulas. A set of formulas is satisfiable if and only if there's at least one state that satisfies it. So you need to show that there is no state that satisfies this set. Note that there cannot be a state that satisfies this set because gamma is here. This set contains both A, so this set, gamma union negation of A, contains both A and negation of A. So if it's going to if there's a state that satisfies gamma union negation of A, that means it gives true to all the formulas in gamma union negation of A. It's giving true to both A and negation of A, which is not possible. Show that gamma is not satisfiable if and only if gamma tautologically implies A for any formula A. This is important actually. If gamma is an unsatisfiable set, then you can prove anything. Or I said again, prove. That's for later on in the course. You can conclude anything from gamma. Gamma tautologically implies anything. An unsatisfiable set tautologically implies any formula, including bottom. When I say any formula, that means it even implies bottom. And this is kind of obvious, right? Because again, if gamma is unsatisfiable, that means there are no states that satisfy gamma. Now, this is vacuously true because this says if there's a state that satisfies gamma, then it satisfies A. There are no states that satisfy gamma. So the argument, the statement is vacuously true if gamma is unsatisfiable, and vice versa. Just an if and only if is vice versa. How do you prove the other direction? If gamma can tautologically prove anything, any formula, how do you show it's unsatisfiable? So assumption is gamma can tautologically prove any formula, so it can tautologically imply bottom, right? Yes? Yes. If it's so in order to prove the other direction, as you said, since it can tautologically imply any formula, it can tautologically imply bottom. A set that tautologically implies bottom is unsatisfiable, because if it was satisfiable, then the state that satisfies it would give true to bottom. It's a contradiction. Prove that if gamma tautologically implies A and delta, another set of formulas, tautologically implies B, then if you put all your hypotheses together, that means take the union of gamma and delta. This is the set that contains all the hypotheses in gamma and delta. Tautologically implies A and B. Again, try to prove this by showing that if a state satisfies gamma union delta, then it satisfies the formula A and B. And I think the proof is kind of obvious, right? You use these two assumptions. Any questions? Is any of these vague to anyone? Yeah, these are pretty easy. Let's move on to our next definition, which is the definition of tautological equivalence. Two formulas A and B are tautologically equivalent if they tautologically imply each other. That is, A tautologically implies B and B tautologically implies A. So A as a single hypothesis tautologically implies B, and B, again, the single hypothesis B tautologically implies A. So what does this mean? That means if A and B are tautologically equivalent, then we have this, the first condition. This one tells me that any state that satisfies A satisfies B. And this one tells me that any state that satisfies B satisfies A. That means for any state, the values, the truth values of A and B are the same. So A and B are tautologically equivalent if and only if for any state V of A is equal to V of B. That is, no matter how you assign values to your proposition, to atomic propositions, their propositional variables, the truth tables are the same. Yes. Sorry? So any set of numbers? No, A is not a set. We said A is a formula. It's A is a formula, and B is a formula. We said that we denote the sets of formulas with Greek letters. A, B, C, those are formulas. Theorem, A is tautologically equivalent to B if and only if the formula A, if and only if B is a tautology. Again, another obvious statement, because they're both saying the same thing. A is tautologically equivalent to B is saying that truth values of A and B in any state, they're equal. But this, if it's a tautology, meaning that V of A is equivalent to B is always true for any state V, this is the same as saying that V of A is equal to V of B. Right? But note that this and if and only if, so you have two directions to prove. Both directions are trivial. If A and B are tautologically equivalent, you want to show A equivalent to B is a tautology, take arbitrary state V. Since they are tautologically equivalent, V of A is equal to V of B. That implies V of A equivalent to B is always true. Therefore, A equivalent to B is a tautology. The other way around or backwards, if A equivalent to B is a tautology, then you want to show A and B are tautologically equivalent. You just have to show that for any state V, the values are the same, but since A is equivalent to B is a tautology, B of A is equivalent to B is true, that automatically implies B of A is equivalent, B of A is equal to B of B. So this is really rephrasing what the tautological equivalence is. Yes? What do you mean if A and B are equivalent? Well, do you mean that if A equivalent to B is a tautology, right? Because this is a formula, right? Yeah, now this could be false or true, or could be sometimes false, could be sometimes true. If it's always true, meaning if it's a tautology, then yes. If we know this is a tautology, if we know this is always true, then A and B are tautologically equivalent. Now, just like satisfiability or tautological implication, tautological equivalence can also be checked and verified using a truth table, right? Last time I talked about how to check tautological implication using a truth table. For tautological equivalence, it's even easier. Yes? Mhm. Yeah. So tautological equivalence and implication. First of all, we do not define. It doesn't make sense to talk about sets of formulas when you're talking about tautological equivalence, right? It's only defined for two single formulas, and it's just tautological implication is just one half of tautological equivalence, right? It's just one direction of it. When you have both directions, A tautologically implies B and B tautologically implies A, then you get tautological equivalence. So it's actually easier to prove tautological equivalences using truth tables, meaning if you have two formulas, let's say this one and this one, A implies B and B implies, sorry, negation of B implies negation of A, you write the truth tables and you look at the columns corresponding to these two formulas, and if they are identical, the formulas are tautologically equivalent. If they're not, if they differ even in one row, meaning that row would correspond to a state, right? That means in that row, the values in those states are different, therefore they're not tautologically equivalent. So if the columns are identical, they're tautologically equivalent, and if not, they're not tautologically equivalent. So that's how you check two formulas are tautologically equivalent. If you had a lot of time, actually, but usually it's a lot easier to argue using states rather than writing the whole truth table. So for example, if you wanted to, okay, maybe I don't know if this is a lot easier than truth table, but let's say you wanted to show that A is tautologically equivalent to A and B, or A and negation of B. How do we do this? Without, if you don't want to write the truth table, then we can call this formula C, right? Now we want to show that for any state V, V of A is equal to V of C. So you pick arbitrary state V and show that V of C is equal to V of A. And the argument might require a few steps. So for example, here, I divided this into two cases. First case is that V of A is true, and the second case, V of A is false. So let's see. So if you first assume V of A is true, and then show that V of C has to be true as well. And second case is when V of A is false. Now, the first case, I'm also going to divide it again in two. So in the first case, you're assuming V of A is true. Now for B, also two separate cases. If V of B is true, then V of A and B are both true. That means V of A and B is true. So we have this part of C. Note that this is C. And if this is true, true or anything is going to be true. So VFC is true. And if VFB is false, then VF negation of B would be true. Now VF A and negation of B is going to be true. Again, true or anything is true. That's it for the first case. If VF A is false, then this is false, because VF A is false and this is also false. So this entire thing is false. This is false, false or false, false. Right? So the argument might take few steps, but it's generally easier than truth tables. And in some other more complicated cases of when you have more complicated formulas, it could be significantly easier to argue without the whole truth table. More exercises. Show that tautological equivalences. Show that tautological equivalence is an equivalence relation. I hope all of you know what an equivalence relation is. And if you don't know, please go check your MATH1090. Or I think 1190 also covers it. You should know what the relation is. A relation is a subset of, when you have a set, if X was a set, you can take the Cartesian product of X with itself, or Cartesian product of two sets. Any subset of the Cartesian product is called a relation. A relation is an equivalence relation if it's reflexive, symmetric, and transitive. Now, okay, this really doesn't, it's not going to be very important in our course, but it's important to note that this, the notion of tautological equivalence is reflexive, meaning if A, reflexive means A is in relation with A, meaning A is tautologically equivalent to A for any formula A, which is obvious. If, by the way, this here I wrote A is equivalent to B is a tautology. Here we know, by just our notations here, we know that it means that A is tautologically equivalent to B. So if A is tautologically equivalent to B, then B is tautologically equivalent to A. Again, obvious. This is the symmetry of the relation. And finally, if A is tautologically equivalent to B and B is tautologically equivalent to C, then A is tautologically equivalent to C. Again, think about this with the definitions. This implies A and B, they have the same truth values in all states. This one says B and C have the same truth value in all states. Put these two together, A and C have the same truth values in all the states. So A is tautologically equivalent to C. All right, these are, again, the proofs are really one sentence, most of them, at least the first two. The third one, maybe 2 or 3 sentences. Now, let's move on to syntax again. So we started with the syntax of propositional logic, meaning how to write the formulas, what's a well-formed formula, purely syntactical, like how to write it, what does it mean, how is it constructed, when is it well-formed string, is it a well-formed string or not? And then we talked about the semantics, the truth values of the formulas and so on. What does it mean for one to tautologically imply or be equivalent to another one? Now we are going back to the syntax, and the reason for it is because we are going to introduce the notion of proof. Now we want to be able to prove tautological equivalences using axioms, because as you can see, truth table, writing truth table is a horrible thing. Arguing like this, also not so much better. In this case, it was easy, but if I had a lot of difficult, especially for tautological implication, we have a lot of hypotheses. You want to conclude something that is a large formula. It's not an effective way to do it. That's why we are going to establish a proof system and show that whatever we can prove is a tautological equivalence, and we can prove our tautological equivalences using our proof system. So first thing to introduce is a definition of substitution, which is going to make sense a little bit later on in the course when I talk about the rules of inference of our proof system. But for now, let's just define it. Suppose you have two formulas, A and B, and you have a variable. It's a propositional variable P, and we write A, these brackets, P two dots or column equal B. Now, this is again a formula. What does it say? How is this formula constructed from A and B? It says in the formula A, substitute the variable P with the formula B. So suppose A was the formula P and Q. B is the formula Q implies bottom. Now, what is the formula P column equal B? As I just said, this is a formula that is obtained by substituting B for P inside A. So you have the formula A, which is P and Q. And in this formula, if you substitute P with B, what do you get? You get B and Q. What is B? Q implies bottom. So this formula is this formula. So we're going to use this. Oops. Sorry. This is this, which is the formula. Now, yes. Yes, that's what it means. So this is the substitution of B, P with B inside A. Now, yes? This here says which variable to substitute. Yeah, sure. If I replace this with Q, then you don't substitute P, then you have Q, then you get this. No, P, sorry. No, it. What do you mean it shouldn't matter? It's always a unique formula. You don't have a choice. It's given to you which ones to substitute with what, right? You cannot choose I want to substitute P or Q. This one here tells you which one to substitute. Now, this is not a good definition, what I just told you. It's not even a definition, just substitute. How do you define this precisely? Everything in logic or mathematics needs to be defined precisely. You define the notion of substitution as usual by recursion. So let's recursively define this formula, A, the substitution of P in substitution of P with B in A. Now, first you define it for atomic formulas, right? Now, here, if your A is P, it's an atomic one. Now, in P, you substitute P with B. What do you get? You get B. So if A is P, what you get is B. Now, suppose A is any other variable, Q, R, S, whatever, other than P. Now in Q, you substitute, so our A is Q. A is Q. Now here, you substitute P with B. What do you get? Q itself, there's no substitution, right? Because there is no P, substitution doesn't do anything. So what you get is Q, which is A. So you get A itself. Substitution didn't do anything. Now, what if it was top or bottom? Again, top or bottom, they're atomic formulas. And what you get is, again, there is no action done by the substitution. What you get is A itself. So in the case that A is an atomic formula, other than any atomic formula other than P, what you get is A itself. Now, since this is a recursive definition, suppose we have defined a substitution for the formula C, and A is the negation of C. Now, we want to define the substitution of P with B in the formula negation of C, assuming that the substitution is defined for C. Now, you can easily verify that this would be a negation of the substitution done in C. So this is by definition is the negation of substitute P with B in C. Now, in the case of the other four quantifiers and or implies an equivalence, since the definitions are the same or similar, let's just this circle denote one of these four symbols. So let's say we wanted to define the substitution where A is the formula C and D. You're going to define the substitution of P with B inside this formula. by definition, we define this to be, do the substitution in C sorry, not yep, and use the same connective, do the substitution in D. And so on. It's the same for or, implication, and by implication. Yes. Sure, this is a recursive definition. Then recursive definition will take care of that. We'll go back, you go down in the recursion to compute this, you apply the recursive steps backwards, and then you get, if there are no P, then this is not going to affect, there are no P in formula C, then this is going to end up being C itself. But recursive argument takes care of this. This is why you define everything recursively. And then we don't worry about these kind of things, like what if P was not in C? The recursive definition will take care of that. And if, like, really, it's very easy to prove by induction that if, for example, in this formula there's no P, then the result of this substitution is going to give you back C and D itself. We'll talk about that. I'll give you some, well, I think actually that's one of the propositions that we are going to prove. But the first one is the following. First of all, we define this. It's a recursive definition. First of all, what we want to make sure that is true is that the resulting string is always a formula. It's a well-formed formula. And how do you show that it's a well-formed formula? So the proposition is for any formula A and B and the variable P, this is a formula. It's not just an arbitrary string that you obtain by substitution. As usual, as I mentioned, whenever something is defined recursively, you prove statements about that thing by induction. So here, we prove this by induction on the complexity of the formula, because our recursive definition was by recursion or induction on complexity of the formula. So how do we prove this? Prove by induction on the complexity of the formula. First, when formula A, by the way, not on the complexity of formula B. B is a fixed formula. We're going to fix B. Proof is by induction on the complexity of A. So first you assume A is an atomic formula, and you show that this is a well-formed formula. So the statement holds for atomic. If A is an atomic formula, then by definition here, these three cases correspond to atomic when A is an atomic formula. The substitution is either A or B. And we started with formulas A or B. So the substitution is a formula itself because it's either A or B. So that takes care of the atomic case. Now you're assuming, we are going to assume that the statement is true for the formula C, for two formulas C and D, right? So we are going to assume, maybe I'll write what the inductive hypothesis is. I've written it here. Here, this is a formula. Also, this is a formula. So both of these are formulas. Now you want to show that if A is negation of C, the statement is true. So we know the statement is true for C, meaning that we know this is a formula. We want to know that negation of C, the substitution, this is a well-formed formula. But by definition, this is negation of the substitution done in C. The negation, we know this is a formula. Negation of a formula is a formula. So it's a well-formed formula. Similarly, now we are assuming that the substitutions for C and D are well-formed formulas. Now A is C a connective D. So for example, if A is C and D, then we want to show that C and D is a formula. Right, this is what we want to show, but we know this is by the recursive definition. This is C substitute P with B, and in D you replace P with B. This is a well-formed formula. This is a well-formed formula. A well-formed formula and conjunction here with the well-formed formula is a well-formed formula. Therefore, now we covered all the cases. The proof was obvious, but again, it's about practicing the proof by induction. And perhaps less obvious proposition would be the following, that it's actually the question that one of you asked, that if P does not occur in A, then for any formula B, the substitution of P with B in A is just A itself, right? If there is no P in A, now substitute P with B inside A. There's no P, nothing happens, right? So it should give me A by our intuition, by how we understand substitution. But how about the definition? Is the definition doing the same thing? Definition is doing the same thing as we expect. It's a literal substitution of P with B inside the formula A, but done properly in a mathematical way. So why this is true? Let's prove this by induction. Again, induction means it's induction on the complexity of the formula A. B is a fixed formula, P is a fixed variable. Note that we are showing this statement is true for any P and B, right? So fix your formula B, fix your variable P. Now, if A is an atomic formula, then an atomic formula is either a variable or a constant number, right? Now, if A is P, then P does occur in A. But we are assuming P does not occur in A. So P cannot be P, right? So P is an atomic formula, but we are proving this for the formulas A that do not contain P as a subformula. That means P does not occur in A. So A cannot be P. That leaves us with the rest of the atomic formulas. That means top, bottom, or any variable other than P. In all those cases, the substitution is defined to be A itself. That corresponds to this. Note that A cannot be P in the atomic cases. Let me write this atomic here. We're left with two steps. In both cases, the formula, the substitution is the formula A itself. And this is what we are proving, that the substitution is A itself. Yes? Empty set, but we're not talking about sets. Empty, I think you meant empty string. Empty string is not a formula, right? We just proved that substitution always gives you a formula. Empty string is not a formula. So no. So that concludes the basis step, right? So what in the basis step, one more time. We are assuming A is an atomic formula. That means it's either a variable or a constant, but it cannot be P because we are assuming P does not occur in A. And in all the remaining cases, the substitution just by the basis step of the definition itself is always A. Therefore, we get A. Now, the inductive step. We are going to, again, take that the statement is true for formula C and D. What does that mean? That means the inductive hypothesis is that if P does not occur in C or D, then okay, this is a little bit bad way of writing this, but I just wrote it anyway. So this is C. So what I actually should have written was that for any formula of complexity less than complexity, a fixed complexity, say n, if P does not occur in those formulas, then the result of the substitution of P with B is always the formula itself. But I think this is clear enough. But let's continue. Suppose now A is negation of C. Note that here, really, it's about this C here. A is negation of C, and C has a complexity 1 less than complexity of A. So it falls into our inductive hypothesis. We know that if P does not occur in C, then the substitution of C is going to be C itself. Now, do we know that P does not occur in C? Well, we start with A that P does not, we take A's that P does not occur in A. Now, if P does not occur in A, cannot occur in C as well, because A is negation of C. Right? So we are proving this in all the cases, A is a formula such that P does not occur in A. And now P does not occur in A. I know that P also is not going to occur in C. So inductive hypothesis applies for C, meaning the result of the substitution of P with B is C. Now, the substitution of negation of C, P, B by definition is negation of, do the substitution for C. So it's the negation of this. But this, by inductive hypothesis, is C. So what we get is negation of C, which is, negation of C is A. Right? Oh, this is B. Sorry. Thank you. Yep. Now here, for when A is, C implies, let's say, implies D. Now, P does not occur in A. It means P does not occur in C or D. So I don't know if I should write and or. C and D. It doesn't occur in any of these two formulas. Now, the substitution of P with B is, in the formula C, substitute P with B, which is by definition, by the recursive definition, this is, do the substitution of P with B in C, and this implies the substitution of P with B in D. And since P does not occur in C or D, by the inductive hypothesis, so let me change the color. By the inductive hypothesis, this is C, right? This is the inductive hypothesis. These two, this is C, implies D. Which is A. We're done. In all the cases that we considered, if P does not occur in the formula A, the result of the substitution of P with any formula B is always going to do nothing. You just have A itself. Yes.
Can you explain why you said that P has a complexity of 1 less than N?
Well, it's clear, right? What's the complexity of, let's say complexity of A is N. And what is the complexity of C then? No, it should be N minus 1, because if this is N, then this adds complexity 1. So it should be 1 plus N minus 1. Right? The complexity of C should be N minus 1. So what's the complexity of, let me write this here. What's the complexity of this? 2. So now let's say this is your A. And now this is A is negation of C. And this is your C. Now what's the complexity of C? C is P and Q. C is P, sorry, I thought I wrote Q. C is P and Q. It's just one, right? So you add a complexity by adding a negation. All right, any questions? Any other questions? All right, now let's have an example here. A is the formula, P and Q implies negation of Q is equivalent to bottom, and B is the formula, negation of Q or R. What is the formula A when you substitute the variable Q with the formula B? So this means in the formula, P and Q implies negation of Q equivalent to bottom, substitute P with B, with the formula, what was B? Negation of Q or R. Now by the recursive definition, this is a formula implies another formula. So this substitution is done here in P and Q. You do not have to do this in the future, but I'll do it once, so we don't have to do this in the future. To check that recursive definition is going to give us the literal substitution. Now, if you apply this further, this substitution is the substitution of P. Inside P, substitute P with negation of Q or R. And inside Q, substitute P with negation of Q or R implies negation of Q. I'm going to skip some of the steps at least. Substitute P. I'm going to need a large bracket here. P with negation of Q or R is equivalent to substitute P inside, sorry, in the formula bottom, substitute P with Q, sorry, negation of Q or R. Now, what is this? In P, you substitute P with negation of Q or R. The recursive definition, P is atomic. Now I can use the definition. This is negation of Q or R. And what is this? In Q, substitute P with something. P does not occur. Q is atomic. I know the result of this is just Q. Note that the priorities of brackets, they tell me brackets are here. I know that. Now this implies, what is this? It's the inside negation of Q, substitute P with something, that is negation of inside Q, substitute P with something, but the substitution doesn't do anything again. It's negation of Q. And here it's equivalent to, what is this? Again, P does not occur in bottom, the substitution doesn't do anything. You see, what we got was the literal trans. You don't, in the future, you don't have to do this because a computer will go through this step to do the substitution, but you don't have to, because now we know the way that we define the substitution is a literal substitution. Just whenever you see P, substitute it with the given formula. But what I did was the recursive step, go back all the way back down to atomic, and now you have the definitions for atomic cases. You replace them, and you do that. One remark about the syntax of this substitution. In a substitution, this operation, by the way, it comes from the meta theory. It's not part of our alphabet, but it has the higher priority than any other thing. For example, if I wrote P, A and B, substitute in A and B, substitute P with the formula C with no brackets, because it has highest, the substitution has a higher priority. It means this. A is outside the substitution. Here, where? Oh, sorry. Did I make a mistake? Sorry. I made a mistake somewhere. Sorry. 1 second. What was the general formula? Oh, we are substituting. Okay, I proved something else. Sorry about that, because this is not the question. I proved this. I forgot that this was a substitution of P and not Q. What I proved was a substitution of P. I forgot that we were substituting Q, but that would remain as exercise. So this is a substitution of P with B in A. You do this one yourself. All right. Are there more questions? Right. If not, have a nice day, everyone, and see you next week. Okay.